Emostel.
Hello everyone, how are you doing now? So this is the third video we are doing on vectors, still under the study session 1, and it's going to be the final video on vectors anyway. Alright, previously we talked about the addition of vectors, we talked about the components, and then we discussed the addition of vector in terms of its Cartesian coordinates, and then in terms of its polar coordinates. So I've just made a summary of all our discussions so far in terms of addition of vectors. I've just made it here. So this is the graph for the polar coordinates, and this is the graph for the Cartesian coordinates, where vector R is a combination of what? The x value, whatever it is here, okay, and the y value, okay. That is it. So, which you can as well represent that the x value, let's say x is 4, here is 8, and stuff like that. And then which you can also represent in form of xi plus yj and all that. Okay, and then the magnitude or the size of the vector can be represented this way. And the same thing, Rx is a component here which is given as r cos theta, ry is given as r sin theta. So you can also add the addition of the vector or the resultant of the vector is given as what? The effect of Rx plus the effect of Ry. That is the general effect on R, okay, which forms the addition of the two vectors. Addition of the vector is called the resultant vector. This is the resultant vector. That is the resultant of the effect of the joint vectors Rx and Ry. Okay, you can take it as the effect of Rx and the effect of Ry overall the effect of the two vectors. Let's assume this is a point and you are pulling it this way, you are pulling this pole this way, the overall effect of the two of them is called the resultant vector, represented as what? The effect of the Rx and the Ry effect together forms this. So you can relate it as this is the effect of R on this plus the effect of R on this. Or you can relate it better still as this being the overall effect of this and this on this point. Do you understand? So everything is just like overall effects. Okay? So, and then this one here too, since Rx is R cos theta, Ry is R cos theta, so you can also represent, you can either represent this way or you represent it this way, because Rx is equal to R cos theta from here, and Ry is R sin theta from here. So, put it this way and put it this way, you are still correct. But if you want to find the magnitude, to make it easy, work directly with the Rx and Ry components, square each of them, and then you get the magnitude of the vector. So it's all as simple as that. Okay? And then remember to find the direction. Okay, you just make the x component divided by the y component, give you the direction of the vector. And the x time, the inverse tangent of the ratio of the x component and the y component gives you the direction of the vector for a two-dimensional plane. And so that's that as to that. Let's quickly move on to a scenario in which we have the three-dimensional plane. Let's say we have three axes: the z-axis, the let's say the y-axis, the x-axis. Each of the axes are 90 degrees, okay, to each other. Like z is 90 degrees to y, that's perpendicular. So you can see you're having this scenario, this kind of scenario like this. This is an axis, the z-axis. This is another axis, the y-axis, and then the x-axis. So all of them are perpendicular to each other in each case of the area covered. Okay, so as you have it this way, let's say we now have an overall vector coming out just like this marker coming out like this from the three of them, and this guy is just projecting outward as the resultant effect of the three vectors. Okay, so vector R. So which means if you trace this guy down to the x-axis, the value it gives you here stands as x. Okay, if you trace it here to the z-axis, the value it gives you from here to here stands as the z. And then if you trace the same guy here to the y-axis, from here to wherever it stops, the value it gives you, let's represent that as y naught. Just the same way you did Rx and y as R is equal to xi plus yj. Right? The unit vector along the z-axis is represented as k. I for x-axis, j for y-axis, and k for z-axis. So in the same way, you could also represent x, y, and z for a three-dimensional plane, okay, as what? R as this xi plus yj plus zk. It is also be represented that way. You understand? So it's just as easy as that. And then to find the magnitude is still the same thing, okay? So which means the overall effects of R, okay, is equal to the sum of the components of the sum of the effects of the components on each of the three axes. Okay, so the component of this vector on x-axis is xi here, represented as x naught. Okay, so how many units we count across the x-axis is what we're going to put here. The y-axis too, how many units we count across the y-axis from here, from the origin to where it stopped here, is what we are going to put here. And then how many units across the z-axis is what we are going to put here. For the unit vector on each axis, respectively I, j, and k. So if you want to find the magnitude, it's still the same way. The magnitude of R in this case of three-dimensional plane is going to be equal to x squared plus y squared, okay, plus z squared. And so you get it? So that's how it goes. Now that is for three-dimensional plane. Then, how do we find unit vectors? Let's see. A unit vector, we see, in general, every vector R is equal to the product of its magnitude. Like I told you, you can either put the bar or ignore it, okay? And its unit vector. The unit vector is represented by a kappa sign. Every vector R is equal to the product of the magnitude of the vector and the unit vector. Okay, every vector R is equal to the product of the magnitude multiplied by its unit vector. A unit vector is a vector whose magnitude is equal to 1. A vector that has a magnitude 1 is called unit vector. So sometimes we'll be required to find the unit vector. If you make it the subject of a formula, you have the actual vector divided by its magnitude. Okay. The unit vector is equal to the actual vector divided by its magnitude. Okay, let's just play with this for instance. Let's say we are given a vector A to be equal to 2i plus 3j. All right. And the unit vector, okay, there's a way they usually put a question as find the unit vector perpendicular to this, or find the unit vector parallel to this. Okay, but in this case now, we're looking for the unit vector parallel to A. Alright, so we're trying to look for the unit vector that is parallel to A. So to find this, if you are given this kind of question, let's go straight to the point. As you know, the vector A is equal to the unit vector is equal to the vector A divided by its magnitude. So the very first thing you find is the magnitude. Let's get the magnitude first. The magnitude of this vector A is going to be equal to the sum of the squares of 2 and 3, right? So that's 2 squared plus 3 squared, the square root of that. And then we're going to have this one as 4 plus 9, and that will be 13, the square root of 13. Okay? So which means the magnitude of A is equal to the square root of 13. So therefore, the unit vector parallel to A is going to be equal to, the unit vector A is equal to the actual vector A divided by the magnitude of A. You know, I make this guy the subject of the formula and through this one to go and divide. Just as if you say, okay, 2x is equal to 4. You're looking for x, x will stay, y2 will go and divide. So you have x is equal to 4 divided by 2. So that's the same thing I did here, just like that. So I kept this one and I kept this one to go divide. So that is what formed this guy here. Okay, now back to this place. We have the actual vector A divided by the magnitude of the vector A, right? So if you want to put it that way, the actual vector A is what? 2i plus 3j. So magnitude of vector A is given us what? Root 13. Root 13. You can find the root if you can, but let's just leave it this way. So which means the unit vector perpendicular, unit vector parallel to A is giving us 2i plus 3j over 13. And then we can still put it as 2i over root 13 plus 3j over root 13. And it goes. That's the result. Okay, that's the result of the unit vector parallel to vector A. Okay, now, because we told you that the unit vector is a unit vector whose magnitude is equal to 1. So, which means let us test whether truly this answer is correct for the unit vector parallel to A. Let's check if it's actually correct. Okay, to check that, what you do is that let's find the magnitude of this unit vector A. Because a unit vector is a vector whose magnitude is equal to 1. Let's check whether the magnitude of this result will give us 1. Let's check it out. So, the magnitude of the unit vector of A that we just got now is going to be equal to 2 over root 13 all squared plus 3 over root 13 all squared. Then we find the square root according to the formula of finding magnitudes. Okay, just like this. Then we now have, okay, according to the law of physics, this square affects the numerator and the denominator. So 2 is power 2, that will give us 4. Then, now, according to the law of physics, the square root of 13, and the square of the square root will remove the square root. The square of the square root will remove the square root. So because root 13 raised to power 2 will give us root 13 times another root 13. This gives us, right? And according to the law of physics, root 13 is equal to 13 raised per half, multiplied by another 13 raised per half. So if you bring the two together, then according to the law of physics, it's going to be 13 raised per half plus half, and then that's going to be 13 raised per 1. And then number raised per 1 is equal to that number. Okay, if you don't get all this code, don't worry. I have a video on indices. You can just check the link and then you watch the video on that too. Okay, so let's come back home. And so by the time you have this one, 2 is 4, 2 is 4, then the square root of this will be 13. So it means the square of the square root is almost the number under it. Just know it like that. The square of the square root will give you the number under it as a result. Then we have the square of 3 is 9. That's 3 times 3, 9. Then the square of root 13 will give you ordinary 13. And then going forward from here, you have the square root of, you find the LCM. The LCM here is 13. And 13 and 13 is 1. 1 times 4 is 4. And the remaining 13 is 1. 1 times 9 is 9. At the end of the day, we have the square root of 4 plus 9, 13, over 13. And that's the square root of 1. And the square root of 1 is what? Is 1. And so that is that as per that. So truly, this is the unit vector parallel to vector A. Okay, so this marks the end of this video. I've just explained unit vector, or let me just quickly give you a little bit too. Unit vector is just, okay, let's say we plot a vector, we plot a graph and say this is 1, this is 2, this is, as you are counting, for every single unit you count, that is a unit. You count 1 unit, 2 units, 3 units, 4 units, and so on. And that gives you the component. And that's the reason why, if this happens to be 3, because you counted 3 units across the x-axis, you will say what? This is 3I. And which goes back to this formula, which says, because I told you before, that whatever you represent on each axis is a vector as well. Okay, so which means if you have this guy like this, and this is x, this is y, and this is r, okay, and then you come here, this part here is a vector. From here to here is a vector too, because it has magnitude. Let's say from here to here is 3. That's 3. You counted 3 units, right? So give me 3I. It's a vector. Here to here is also what? A vector. The resultant effect of these two vectors is what produced this guy. Or is what is said to have produced this guy. Okay? So vector in this direction, vector in this direction, the resultant gives us here. So the component of this vector, that is the aspect of this vector on x, the power of this vector on x, or the power of x on the vector is from here to here. The effect of y on the vector, on this same vector, is from here to here, which is a component, right? Okay, so if you look at this 3I, okay, 3I means 3 units, or the magnitude is 3, and then I is the unit vector. So every vector is a product of its magnitude and its unit vector. I is the unit vector across the x-axis. J is the unit vector across the y-axis. K is the unit vector across the x-axis. The number here, which is 3, is the magnitude. We sign that by we count 3 units across the x-axis. I know that. I just want to make this make sense. I feel that by now you've actually understood what is really going on, and then just read it, understand it, learn it, and then digest it and apply the knowledge. Solve a couple of questions, practice. If you have any issues, you can always ask me. You just chat me up and then ask me any question you want to ask. I will put you through. And then kind of a lot of practice question and then solve. If you have any question, any issue with any question you're trying to solve, get in touch with me as well. I will put you through further. That is how you learn. Okay, so don't forget our slogan, Emostel Academy. Learn, understand, and then apply that knowledge, and then you will excel. Take care.